Hello everyone, my name is Vishwas. My roll number is 2201CS78. Today I'll demonstrate my assignment, second assignment, Asymmetric key encryption secure messaging app. So this project implements a secure end-to-end messaging system using RSA 2048 for key exchange, AES 128 for message encryption, RSA OAEP for wrapping the AES key, and digital signatures using the SHA 256. So the objective of this project is to securely send a message from one user to another using public key cryptography. And the system has the three main components: key generation, message encryption, message decryption, and verification. So each user has a RSA 2048 key pair. The sender encrypts the message using AES 128 and encrypts the AES key using RSA OEP. And the digital signature is used for authentication and integrity. So this is my project folder. Here I have app py, which is the main program, and we have keys folder where we'll store all the generated public and private keys. So first I'll explain the code. At the top, I'll input all the required libraries, and then we have our generate key generation function. So here we generate our RSA 2048 private key, and then we extract the public key from it, and then we encrypt the private key using the user's password, and then we save both the keys as PEM files, and then it computes a SHA 256 fingerprint of the public key, and it prints for identification. And then we have our loading keys. We have two loading functions. One is for load public key and load private key, which are used to read PEM files from the disk. The private key is decrypted using the user's password. And then we have our encrypt message function. So first we have a random AES 120 session is generated, and a random IV is generated, and the message is padded and encrypted using AES 128 uh, CBC mode, and the AE generation is encrypted using the recipient's RSA public key with OEAP, and then a digital signature is created using the center's RSA private key, and all the encrypted data is packaged into a JSON object. The JSON includes ciphertext, encrypted AES key, IV, digital signature, sender ID, and a timestamp. So this ensures all the confidentiality. And then we have our decrypt function. So here the JSON package is decoded, and the cyber digital signature is verified. And then the AE session key is decrypted using the recipient's private key, and the message is decrypted using AES 128, and then all the padding is removed and the plain text is recovered. Now we will run the program. To run the program, we'll have to go to terminal and then write python app.py. As you can see, the program has been run successfully. So what's happening is first the program is registering our first user, Alice, and it generates RSA 2048 key pair, and the public key fingerprint is SHA-256 hash of Alice public key, and this uniquely identifies the key and helps verify its authenticity. And then we have Alice private keys encrypted using her password before storing it on disk, and both the keys are saved as PM files, which is encrypted private key and public key. So this ensures the Alice private key remains secure even if the file is accessed. And now we have our program registers our second user Bob. Bob also gets his own RSA 2048 key pair, and his private key is encrypted with a password, and his public key and private keys are saved. And at this point, both users have secure cryptographic identities. Now we'll send message. Alice send the messages to Bob saying meeting at 3 p.m. Tomorrow. Now we have our JSON encrypted message package. We have a ciphertext, and this is AES encrypted version of the original message. It is encoded in base64, so it can be safely stored and transmitted. We have our encrypted key. This is AES session key encrypted using Bob's RSA public key with OAEP padding, and only Bob's private key can decrypt this value. So this ensures only Bob can read the message. And we have our IV, which is initialization vector used for AES encryption. So this adds randomness and prevents identical message from producing the same ciphertext. And we have our signature. This is digital signature using Alice RSA private key, and it signs the ciphertext. And this allows the Bob to verify that the message was sent by Alice and confirm that the message was not altered in transit. And we have a sender. This identifies the sender of the message, and we have our timestamp. This is a UTC timestamp showing when the message was encrypted, and it helps with message tracking and auditing. Now we have a receiving message section. User is Bob, and we are loading with the encrypted message. So here now Bob receives the encrypted message. The program loads the JSON encrypted package, and then Bob verifies the digital signature using Alice public key. So this confirms sender is really Alice and the message was not modified. And then we have our decrypting session key. So Bob decrypts the ES session key using his RSA private key. And we have a decrypting message. The message is decrypted using AES 128 and recovered session key. And then we have our final output. And this is the original message. So it is successfully recovered and the message integrity is verified. The message was not altered and the sender authentication is confirmed. So the message really came from Alice. So I conclude this. Thank you.